Hi there, welcome to my workshop. I don't do this ever, so bear with me as I fumble through recording a video, but I just wanted to share some things that I've learned recently. Been kind of tinkering with electronics for the last couple years, just, some circuits and microcontroller stuff. I've been working with the Wilderness Labs Meadow microcontroller a little bit, but sort of the most difficult thing, prototyping things with that has been, well, the most difficult step, I guess, has been actually physically building the board that I know I want to build. Sort of that prototyping step, the physical step it takes forever. So one of the ways you can go about, once you've got a design in mind, is to use boards like this. These are handy little breadboard type boards that you can buy on Amazon, and I don't know if you can see it, but these boards have traces on them, much like a breadboard. If you've ever used a breadboard, you'll know that all the rows on a breadboard are wires, and then you've got these power rails down the sides, and these breadboards come apart in various different configurations, and the bigger and smaller and whatnot. But these particular circuit boards or prototype boards are built to mimic that. So there's a bunch of pre-routed traces here that you can use. Connect to one side here. Actually, you can connect to either side because they're double-sided. But you connect, and not by connecting, I mean soldering. You solder to this hole, and you know that this wire or this hole is connected via that wire underneath. So that's one way. Sort of the limitation with that is you've only got the number of wires here that are pre-printed on the board. Sort of, you lose some real estate with that. So another thing you can do is use these prototyping boards, which are just holes. And these are a bunch of vias stamped in so that you can solder to either side. And then you've got some pads on the end there. Surface pads. Those are not connected on both layers. So you can wire, power rails there. You'd have to wire them all together because they're individual pads. But it makes it nice to be able to, you can use any of these holes however you want. So there's ultimate freedom there, but with ultimate freedom comes all that flexibility comes, you end up with a mess on the back because you have to wire every single trace individually with physical wires like that. So or insulated or uninsulated, still you've got a physical wire that you've got to run in whatever direction. So you've got to worry about crossing over them if it's not insulated. You've got a bunch of things to worry about. But then it becomes a rat's nest on the one side. And you've got different sizes of those, but ultimately if you're going to be building a circuit, you're going to want something a little bit faster, easier to reason about, and so you get and high quality too. But you can get these high quality boards built off of your schematics, boards like this, and they're really high quality. Got another example of a silly design that I made that never actually came to fruition. Well, it did, but that one's broken. But anyway, so you can get boards like that. You can get them made at companies like JLC, PCB, and they integrate right into these tools. When you go to fabricate, you can skip the whole fabrication step on your own and go immediately one-click order, and then you'll have the board in 3 to 4 weeks. Like, it just takes forever. So that's part of what I'm trying to solve is just the lead time in prototyping. So the boards that I'm making are not, professional level boards or anything like that. They're definitely prototype level boards, but they're way faster for me now. So I can go from a design like this, and this is actually that design, printed at home. And when I say printed, I really mean milled. So there's a couple different ways you can go about this. Number one, you need you need copper clad boards. So you can get these off of Amazon. You can see this one's cut out. I've done a couple prototypes over this already, and you can see some of this one was just a boarded job, but you can get these little double or big, small or large, double-sided copper-clad boards. You buy these on Amazon or anywhere. AliExpress, I'm sure, has them too. I actually don't think they have very many of them, but what this is a wafer of fiberglass. I believe it's fiberglass. Fiberglass wafer clad in copper. And so what you do is you start with the blank, and based on your design, you actually send instructions to a CNC milling machine to actually very precisely isolate these pads and leave yourself with the design that you have here in Easy EDA. And so what that gives you is this rapid prototype step, but the board itself is the exact board that you want. It's just, it may not be the perfect quality, but you can take this and you've already got the schematic and everything, and you can redesign another circuit board to send off to the printer. But in the meantime, you can quickly get to a prototyping stage without having to worry about the rat's nest and the craziness. And actually, like these, if you mask them appropriately, and insulate the wires and all it, or the traces, something kind of like this, it'll. I see no reason these wouldn't last the same amount of time as a professional circuit board. It's copper. It's got UV solder mask and everything the same. So theoretically, you could use these, for the rest of their. I don't even know what their foreseeable life would be, but yes, they may not look great, but they are functional, and that's all that really matters in the prototyping stage. So sort of, I don't want this video series or tutorial or whatever to, first of all, I'm not qualified really to speak to circuit design. I'm only a hobbyist in this, so what I do want this video series to be is just a instructional and getting anybody up to speed to be able to do what I'm doing right now, which is just creating circuit boards at home with a CNC machine. Some of the tutorials I found were old or disjointed, or they did things differently, and I just didn't like them. But so sort of one of the things, like I said, I don't want to talk about circuit design too much because I'm not qualified. So, but what I do have to mention is that there's a certain a set of design constraints, I guess, that or I don't know how to put it, but I'll do things in this type of board that I wouldn't do in a production quality board, I suppose. I haven't actually built any boards that are in production anywhere, so I take that with a grain of salt, but I think that I can pretty confidently say that these are not using best practices, right? So I know that, for instance, when you do high-speed USB communication, Brian Kostanich has a good PCB and schematic building tutorial, and he mentioned you have to run high-speed USB communications, the traces close to each other, and there's special tools in Easy EDA to do that. I'm not doing any of that. This is just an adapter board, you can see. This isn't really doing anything special. I don't even know if I could do that with an at-home PCB. Maybe. I've got some really small milling drill bits that 0.1 millimeter, but for what I'm doing right here, and the design constraints seem to work best with. I'll just show you I like to use 2 millimeter track width and 0.5 millimeter for your clearance. And then you see I have 0.498 here. There's just some rounding issues going on with the checker. So I'd like to put 0.498 if I have to, but I like to make 1 millimeter holes. So the vias and the drill diameter and everything is 1 millimeter. And you see that reflected here. And so part of what I'll do is, I know I've already got this done, but what I will do is I will increase the size of all the pads to be 2 millimeters. These are also 2 millimeters. Now the vias I run for a different reason. So when I first got started trying to learn how to do this, I started with single-sided circuit boards. Actually, I have one here. So this is very similar to the other circuit board I was just showing, but it's only got copper on one side. And so these will work. And so you can see here on the design, I've got the blue area is the bottom layer. All the blue is bottom layer. So theoretically, you could design a circuit all on the bottom layer. All the traces are on the bottom, everything. And then you put all your components on top. It's a through-hole circuit, so you solder everything on the bottom. And as long as all the components are on the top and the soldering all happens on the bottom, that all works perfectly fine. Because you don't need to solder anything to the top layer. There's no copper there anyway, but you don't need to attach anything to it. Solder won't stick to this material, so you couldn't really attach anything to it. And also, there's no connectivity there. It's all insulated material, so there's no way to use both sides of the board for traces. And sometimes that's necessary, especially when you're using through-hole components like this. And that's why I picked this as an example, because I feel like it's a great example to show that sometimes you need two sides on a circuit board in order to solder things. It's not just a convenience for routing. It's because I'm going to put this component on the top. I'm going to put these components on the top, and so they're going to cover those areas, and that's okay for this side because those get soldered on the bottom. But for these components, and you see I messed up, I got a missing little piece of metal here. Anyway, for these components, the soldering actually happens on the top, and it looks like everything would work fine, and you can print out a circuit board like this. You can order one like this, I should say, and the top is connected to the bottom, and they do so with a via, and the via is right where your pad is. So this was a meadow layout for the meadow board, and each one of these is just a hole, just like these. And so what you would do is you solder this little these header pins on, just like that. But you don't solder on the bottom, you solder on the top. So if you can't use this board because that is going to go on like that, and then what you have a hole there, but there's nothing to solder to. There's no metal there, and solder won't bind to this plasticky whatever fiberglass. So you can't use one-sided boards when you have to solder on both sides of the board. So you have to use two-sided. Now the problem is when you buy a two-sided blank like this, it only has copper on this side and has copper on that side. It's two-sided, but there's nothing in between. There's nothing connecting those two. So if you solder something here, this is a whole plane of copper, and the bottom is a whole other plane of copper. So you have no connectivity between layers. So what you have to do is use vias, and this is something that people do anyway when they're connecting layers in their circuit boards. These are vias. This is a two-sided circuit board that I had printed. It's got solder mask on both sides. This one doesn't have solder mask, but it's still a two-sided circuit board. And I have driven out in these vias here. But the difference with this design and this design is that these vias are the right size, and I can solder through them, and everything works great. But they're impossible to find. Eyelets like that you can get in there. I don't know how they're doing this in China. I'm sure they're not using eyelets. They're probably, they just have a fabrication method for it. I don't really know. It doesn't matter. It's just, it was impossible for me to find anything like that. I did find a bunch of grommets or eyelets, whatever you want to call them. And I am using them, but they're not the right size. I can't fit certain bigger components through them. They're 0.3 millimeters in thickness on the inside diameter. And when I I have a 1mm tool. That was the only tool I could find, is 1mm thickness. So I'm splitting these grommets, and they're completely useless. I can't stick things through them. But what I can do is use them as a quick way to connect layers. And so what I do is, and this was sort of the big aha moment, and this is why I really wanted to share with people, because I feel like this is what's missing from a lot of these tutorials. And there was one guy that was doing something like this with some EDM wire, but that was like 8 years ago, I think. So anyway, what you do is, so if you were to look at this design, we're looking at this from the top, and this bottom layer is run on the bottom, but it's laid out the same, such that I can punch through right here. And if this is metal, then I fill it with solder, and it touches this pad, and it touches the blue part on the bottom of that pad. Now these two traces are connected. So when I solder on the top here, the electrical connection comes over to this via, goes through the board down to the blue area, and continues on. The electrons will continue on there. And so it's just a really good way to, and you'll see that in Brian Kosnich's tutorial as well. He lays vias out all over the place and connects different planes and everything. And it's a really neat tutorial. You should watch it. But doing that at home, I was unable to use those tiny. They're actually 0.9mm on the outside rim, and 0.9mm on the outside rim of the inside, and like 1.3 on the outside rim of the outside, and then 0.3 on the inside. It was like way too small to even stick a resistor through. I think that's the only thing I could get through, was like a really thin resistor wire. But these particular pins won't go through the actual grommet. So I just had to use them as kind of like a metal filler. Just bang them in there and fill it with solder, and then they're connected. But you could easily do it with like a solid core wire or anything. Or just fill it with solder. As long as you can touch both pads, it'll all work fine. And then you can solder on the top here, but have the trace go on the bottom still. It's really neat. So that's sort of the necessary talk about what steps are necessary to do differently when designing your circuit for home production versus if you're going to just send it out to JCL, JLC, PCB, or some other PCB manufacturer. You can make the traces really thin. You can do a lot of different things. You don't have to have the vias if you have the hole already, and that hole is going to touch both layers. There's no reason to create this extra via if you don't need it. But there are reasons to use vias, otherwise. But it's not for this. Not for just prototyping, because you don't have the right hole size anyway. So that's that for design. So once things are designed, you move on to the CAM step, the computer automated manufacturing step. And that's done in a tool called FlatCam. FlatCam is an open source application. I can't remember the guy's name. I think it's Jose or Jorge. Anyway, wonderful tool. I recommend getting the beta version 8.994. That's what I'm going to be using for this demo. It has scripting in it, and I do have a script that will kind of make this a whole lot easier. In the previous video, I went through all these steps manually, but I'm going to go through. I'm going to use this opportunity to look at that script instead, because these steps are manual and they're really tedious. Okay, so I've got this script, and what does this script do? So there's a couple things that have to happen when you're milling a PCB or a printed circuit board at home. It's not really printed, I guess, when you're doing it at home. It's a milled circuit board. So you have to take your design, save it to Gerber Files, which are just files that describe everything you've designed, really. They have all the pads, they have all the holes, it has the bottom layer, the top layer, the whole board outline, everything is all separate in different files. So you take those files, you import them into FlatCam, which is what this is doing here. It's opening all of those files, and it's doing so from the temp folder, just because. It's also opening, so it's opening Gerber files, and you have Gerber files, and you have Exelon files. Exelon files are just drill holes, basically. Not really sure why they're separated like this, but here I am opening the drill file. So now after these 4 steps, I've got the top layer, the bottom layer, the board outline layer, and all the holes that I need to drill. And so one of the big things you do with a 2-sided circuit board is, well, you flip it over, right? You have to mill on the top, to put all the holes in, and then you have to flip it over, get it aligned just right, and then mill the whole bottom because you've got the traces, and they all need to line up perfectly. So one of the things you do is you have alignment holes. And what that lets you do is you put these holes in there, and then the code here, you see it's specific for alignment holes. It mirrors on the x-axis in this case. So what that's going to do is I'm going to add at 0, -1, which is, -1 on the y-axis, and then 1 over from that. Actually, I have to go 2 over because it's a 1 millimeter drill bit. So if I go 2 over, still -1 on the y-axis, I now have a hole at 0, -1, which is right below the border, the board outline, and then 2 over from that is another hole. And then what the alignment hole tool does is it mirrors those on the axis based on the board outline. So it flips and goes on the other side of the board outline and puts the same 2 holes there mirrored, so that when you flip the board on either axis really, now you have holes that you can line up your drill bit manually and kind of move the CNC machine so that it's in line with that hole. Now you know that hole is supposed to be 0, -1. Now you go up 1 and you're at the origin, or you go over 2 and you look for the other hole and you line that hole up, and now you know you have 4 holes to do this with, and you go back and forth to all 4 holes after you flip it, and you have to actually get all 4 of those holes lined up perfectly before you move on. And then this is how you do it. This is how you set those holes up. So I'm going to run this script in a minute, but I'm just going to go through each step. So then the next step is isolation of the top layer. It doesn't have to be the next step. Some of these are out of order. It doesn't matter. But so you have to isolate the top layer, which isolation on a circuit board is just telling the tool to go and make these cuts, really. It's saying isolate that trace that I created. Cut around it so that it's isolated from the copper in the other areas and the copper here. It doesn't remove all the copper, it just isolates this trace. So you can see here, there's still copper over here, but that particular trace is completely isolated from that. It's actually got a physical space between it. And that was because of this step, this isolation step. And I know that my tool is a half of a millimeter thick. I want to take 3 passes with 50% overlap. Some of this I can explain once I've got it all on screen, but I'm going to move on. So the next step is mirroring the bottom layer. And this is really important because when you design your circuit, you're looking at it from the top down. So all the traces that you can see on the bottom in blue are actually going to be flipped around and mirrored depending on which way you mirror or which way you flip. So because you've got the alignment holes, you can realign this board so you're actually going to have it on here on this big thing, and it'll be cut out like that, and then you flip it over and you realign it to those holes. One there. This is I did this one differently, but then you actually not just have to align it, but it actually changes the orientation of those because you're flipping it physically. So what you have to do is mirror the bottom on whatever axis you're going to flip it. So whatever you mirror on the y-axis, then you would flip it on that axis. And so that just mirrors the bottom layers, pads and everything, so that when you come to this next step and isolate the bottom layer and all the tool and everything's the same for the bottom and the top, except for the fact that you mirror the bottom layer first, and then so now all the isolation happens on the mirrored copy. And then the next thing you do is cut out the board. So you've got your holes, you've got your alignment drills, you've got your isolation, your mirrors, and then you cut out the board, and then you actually have to drill holes. And there's like a limitation in this script. I haven't figured it out yet, so that step is actually not quite automatic yet. But so you'll see I'm only going to do the isolation, the alignment holes drilling, and the cutout in the script, and then I'll come back and show you the rest. But so let's say I was let's do it. I'm going to save my Gerber files. All right, so I've got the Gerber files there now. So now the files are there. When I run this script, it'll open them and go through each one of these steps. So I'm actually going to run this. So that did a lot. And I want to come over here to the plot area again, and now you'll see, wow, there's a lot of stuff going on. There's a lot of steps that just happen automatically. So I'm going to go through each one and kind of explain, because I have to actually add the CNC job for the drills anyway. So generally what you'll do is you'll load your Gerber files first into FlatCam, and they're already here. So that's just taking your design and adding it to the plot area so that later on you can run tools on it. And so one of the things that I did was I created alignment drills, and you can find that in the two-sided PCB tool, alignment drill coordinates. You can do all of the stuff that I just did manually in a tool as well. But I'm going to include the script in the video description as well, and the blog post that I have that corresponds to this, so you can read along. But so where was I? We just ran the script, so it created all these things. It's actually easier to explain if I go through them one by one. Probably should have done that. So when you load your Gerber files in, all that does is show everything on the plot area. You actually have the whole point of loading everything into FlatCam is to generate instructions for the CNC. So the next step is to, once you've got your files in there, your Gerber files, your Echelon files, which is the drills, and your alignment drills, you actually have to create geometry, which is to say you want to isolate things, and we did that in the script. So that was the isolation step, was one of them. The top layer isolation was taking the top layer, all of the pads and everything that you designed, and creating instructions for the tool, these red lines. Can I disable some of this? Yeah. All I'm doing is just kind of disabling some things and making them invisible, just so it's easier to talk about. All right. So when the script editor came, or when the script came and did this step right here, this isolate top layer, diameter 0.5, etc., it generated those these red lines here. So all that's doing is a path in 2 dimension. Looking at the top, right? It's a bird's eye view of the board, and it's saying the tool is going to move around here so that it isolates this pad and this pad and this pad, like all of these pads. And not only those pads, but I did the same thing for the bottom layer too. So you've got all of the traces there. You can't really see them right now, but the bottom traces are isolated as well. So what that's doing is giving it a pathway in 2 dimensions to tell the tool where to move the bed and everything, so that it shapes are correct. And then the next thing that the script did, mirrored the bottom layer, created the isolation. You can see the results of that in the geometry. But then the next step is to actually, and it did the same thing with the cutout, sorry. The next step is to actually create the CNC jobs themselves. What the CNC jobs do is, like, if you double click one of these, it's the same exact thing as running that script, and running, generate CNC job is this step. It's all of this in one line, really, so that I don't have to go through and type all of this stuff or make sure that it's all good. It's all in the script. So it tells FlatCam to generate a new CNC job based on the top layer isolation geometry with a tool that's a half diameter long, wide, a half a millimeter in diameter, I should say. All these settings are, you'll see them here in the isolation, or I'm sorry, in the in here. All of these are the properties, and they get translated into CNC jobs. So what happens is, diameter 0.5, Z cut 0.11, or these are all the settings. So in an isolation job, the Z cut has to be about 0.1 to 0.12 ish, so that what that setting actually means is that it's how deep the bit is going to cut into the physical material, and that's the total depth, the Z cut. So what you get is this multi-depth setting as well, and a depth per pass setting, this DPP setting. So what that's saying is, I want to cut at Z, negative 0.11, which is 0.11 millimeters into the board, but I can't do all of that at one shot. Otherwise I'll break my bit. So because if you're going 0.11 millimeters into the board in one pass, and then you try to, even though it's spinning, you try to move the bit, a little bit, it just snaps because it's just too deep into the board. It's not designed for that lateral pressure like that, and it just snaps. And I've broken a lot of bits. So I figured out depth per pass is 0.03, seems to work well, because you could go pretty fast at 250 millimeters per minute, and not snap the bit. So I did the balancing and broke a lot of bits, so you don't have to. And these are the good settings. So now it went through and did all the CNC jobs for the top layer isolation, the bottom layer isolation, the board cutout. And you'll see I've got these commented out. I can't figure out how to do the drills. So I'm going to do them now. Re-enable all the plots so you can see everything. And what I'm saying I'm going to do is the CNC job creation for each of the drills, the drill geometries, I should say. Because all we have are XY coordinates for where the drills need to go. We need to actually translate that into a three-dimensional coordinate system and say, hey, CNC machine, I want to go to this XY coordinate, but here's how deep I want to go, and here's how fast I want it to spin, and here's how fast I want you to go that deep, and here's how many passes I want. You might actually want to drill and back out, drill and back out, drill and back out again, and all those settings are here. And there is a script. It's not CNC job, but it's, it's drill CNC job or something, but I haven't been able to figure it out yet. So this step is so minor. You just come here and you double click on the board outline alignment drills. Here is the one that's these holes. It's really just, it's already set because the script actually created the Exelon object or loaded the Exelon object. And now all you have to do is come into the drilling tool and actually generate the CNC job for it. Everything else is pretty good. Drills are easy. So do the same thing for both of these. The drills were from the file that got loaded, which are all the vias and all the actual pads that get drilled through. It's the same settings here. Everything's good. But now you'll see there's a line which indicates that the CNC machine is going to, move the head to that location and actually go down and drill. And all those lines actually have 3 dimensions encoded in them. So I think that's everything. Went from PCB design. I talked a little bit about the different considerations for designing circuit board this way for home use or for prototyping versus something that needs to be high volume or really high quality. But and then I walked you through a little bit of the CAM process, getting to the point where we've got CNC jobs. And so I guess the final step is it's already done for a lot of the other. It was done in the script for the other jobs. I forgot to do it for the drills. Each one of these actually has a physical file that you need to save so that you can send it to your CNC machine. And because I was using the script, it was all saved in the temp folder. So if I really wanted to be to show you the right location, it's here. But I could save this drill CNC job here in the same place as the other ones. And then the board alignment drills as well, same thing. So now, if I copy, well, it doesn't matter. Save that. All these files now, you get to send them to the actual CNC machines. This is the G-code. This is the language that the CNC machine actually understands. Let me actually open one of these. Top layer isolation. Now, this is not a requirement to understand, but I think it's important to see what we just did. Ultimately, the only thing that we were looking to do is generate a set of instructions that we can send it to this little machine over here on my desk to, operate all the motors and move everything all to the right places such that is going to generate what we want, the circuit board. So these are individual instructions. So what the program called Candle does is it goes through this file and communicates with the board that's on the CNC machine, the actual, the motherboard, the actual machine. It communicates with the machine and says, goes one by one to each one of these at the rate that you've asked it to go, and it just tells it to go to each one of these places and do each one of these instructions. So G1 is go, M3 is set the spindle speed, G00 is go here as well. I think there's other ways to go. I think one of them might be relative, one of them might be absolute. Doesn't really matter. But it's a lot. Let's see, I'm just trying to get to a different instruction. So you can see it got to kind of a stopping point in some of its instructions here. And it goes and it changes the spindle speed again, or I don't know. No, it changes the feed rate, I'm sorry. And then it goes to all the way to negative 0.11 for some, I don't know. It just does all this stuff. we generated all this, and we don't have to do any of this by hand, and it's just a beautiful thing. I just thought it was important to see. And the end result is that it goes back to Z30, and you get to change your tool and go to the next job and load the next file, etc., etc. So that's that. I hope that was helpful. I will be moving on. The next video, I'll be moving on to Candle and actually, taking the instructions that we generated in FlatCam and moving on to physical fabrication, so we can actually see the CNC machine moving. And I'll try to get some recordings of it, the final product, and all the maybe some high speed or time-lapse video of the thing working, doing its magic. But and then after the fabrication itself, you got
I guess part of fabrication that I haven't figured out yet too is the UV masking. I mean, I figured it out. It's not hard to paint on already soldered board, but when I say I haven't figured it out, I haven't figured out how to make it look good like this yet. And there are ways to use screen printing to do that. I think the biggest tip I heard was to dilute the UV mask with a little bit of alcohol first to thin it out. I'm going to try that, but I haven't perfected that process yet. But I felt like it was a good point to share what I have learned and perfected, and which is, all the way from start to finish. I can create an actual prototype board now. So anyway, thanks for watching, and we'll talk to you next time.